Welcome to this video number 2 on load flow analysis. In this video, we shall continue with our first learning outcome, that is load flow problem. So in the previous video, we have seen what is load flow. Load flow is nothing but power flow, and to have a power flow into the system, how power flows into the system, if you want to understand, then we need an equation what is called as power flow equation. Now, when the concept of equation comes in our mind, we come across the concept of variables. Suppose, for example, if I have a equation y is equal to 2x, then we can say that in this equation we have two variables x and y. X is independent variable and y is dependent variable. So if you want to develop any equation, power flow equation, then we need to define some variables. In the load flow, uh, four variables are defined, and these are with respect to each of the bus in the power system. The first variable, it is active power. So what is this active power variable defined in the power system? Suppose if I have a bus in the power system, already know what is bus. Bus is a juncture in the power system where transmission lines are interconnected. So suppose if I have a bus and say that there is a generator connected to this, and say that the generator is giving a active power Pg into the system, and it is giving reactive power Qg into the system. Now there is a load also connected to this system, and this load, say it is taking a, a real power PL and a reactive power QL. Now we can see here some power we are injecting into the system and some power we are fetching it out from the system. So now the question is, what is the net power? What is the net power that we are injecting into the system? Net power. Now let us have the net power Pi. Okay, let real power, net real power injected in the system, it can be defined as Pg minus PL, where Pg, it is the generator real power injected in the system, and PL, it is the load real power. So the difference between these two will give you the net real power injected in the system. Similarly, the net reactive power injected in the system can be calculated by Qg, reactive power injected into the system, and QL, the reactive power taken from the system. Now this P, we can say this P, what it is called as, this is taken as active power variable, and Q is taken as a reactive power variable into the system. So it is to be understood that these variables, active power, loosely speaking, I have written it as active power, but specifically it is a net active power injected into the system. Similarly, the second variable is net reactive power injected into the system, which is actually Qg minus QL, and net active power, it is equal to Pg minus PL. Then the third variable, it is voltage magnitude, that is defined at the bus. Now at this bus, what is the magnitude, what is the voltage at this bus? So magnitude of that and the phase angle associated with this, these two are taken as another two variables. So these are the variables defined for developing power flow equation into the load flow problem. Now let us look at the constraints on load flow variables. Now we know that there are variables P, Q, V and delta. But all of these variables, they are constrained due to some limitations. So what is the first? It is a generation limit. What is generation limit? That every generator into the system, they are designed to operate at some rated power. So the minimum and maximum real and reactive power generation from the generator impose limit on the load flow variables. As P minimum, P value, it should be greater than P minimum and should be less than P max. Okay, so it is to be understood that here generator, they are rated to give some fixed power. We cannot expect power more than that. So that put limit on your variables. The second one is voltage limit. All of we know that the equipment in the power system, they are designed to operate at some fixed voltage. For example, at our home, we are expecting 230 volt fixed. There may be some variation, like it can go to 440 or it can fall down to 210 also. But this is our fixed value. So there is certain band more than 230 and less than 220, but we cannot expect a very high value or very low value. Our equipments are not designed to operate at that voltage. So because of this, the voltage in the power system, they must remain close to some rated values. So these also put a limit on the voltage variable. So we are expecting that the voltage in the power system should be greater than some V minimum and should be less than Vmax. Then the third limit, it is the phase angle limit. It is because this limit arises because of the stability point of view. We know, we already learned in the power system subjects that uh, the maximum stability limit, that is for delta, steady state stability limit, delta is equal to 90 degree. So whatever phase angles we have in the that is with respect to voltage, that should be less than this 90 degree, so as to so that our system will remain stable, and this puts a limit on variables. So delta should be less than delta max. Next one is transformer and transmission line are not overloaded. We know that transformers, they are also rated for to operate at a fixed voltage, and transmission lines, in the previous examples we have seen that if we are operating it beyond its capacity, then it may cause damage. So that also put limit on our variables. The next one is the power in the system to be balanced. This is very, very important, that in the power system, whatever your generation is, that total generation in the system should be equal to the total load plus total loss in the power system. So this is called as power balance equation, and this hold also good for reactive power, like total reactive power generation should be equal to the reactive power load plus the total Q reactive power loss into the system. So this is called as complex power balance equation. The power balance equation is simple word, that the total reactive power, the total, if you add up all the reactive power, it should be zero, as well as the total reactive power, it should be balanced, like here as per this equation. Okay, so these are the constraints that we should understand. They put some limitations on our variables. We cannot choose the value of these variables P, Q, V, and delta as we wish, but they have to be in certain limits. So in certain sets. So this up to this only. So here I have written P gen equal to P load plus P loss, Q gen is equal to Q load plus Q loss. Okay. So in this video, it is up to this only. So I shall continue in the next video. Thank you very much.